here's where we are.
It was, but I hated the timer went off and I'm like, oh. The only problem is we did not want to shop. We get 5 minutes or like 10 minutes. And so by like, I didn't know how much of our 15 minutes. I was like, we got to answer the question. Like, I don't know.
Okay, y'all. Here's where we are. We're not going to talk about coordinate covalent. Metallic compounds we don't talk about much. But what are they? Metals, nonmetals. They're made up of metals and no nonmetals. Covalent. What do they do? Huh? Only. Yes. And then ionic compounds. That's still where we are. And I call these, they're simple ionic compounds. And then transition metal ones. So simple is what we were going over last time. Oh, do you have your periodic table from last time? You still got that to look at. I mean, we have that one on the wall, but not everybody can see it. Okay, here are the simple ones. What's the charge on magnesium? What's the charge on chlorine? Charge on chlorine. Charge on chlorine. You guys, charge on chlorine. What's the charge on chlorine? Huh? I didn't hear you. Does anybody have their periodic table? I'm expecting that you're looking.
What's the question?
You don't memorize them.
What's the charge for?
No, you count to the right.
Oh.
Don't count chlorine, but count to the right. What do you get?
Plus 1?
Yeah, it's -1.
That's what I meant.
So if you're looking at chlorine, chlorine, count to the right. There's argon, there's a xenon next. You count to the right and it's 1. Charge on nitrogen is 1, 2, 3. So anyway, so there's that. So now if you're going to make a formula out of these, what's the formula?
You lost me there.
It's this. NGCl2. You remember? This is what we're doing last time. Okay. What's the charge on lithium? On the left side.
Positive.
And what's the charge on nitrogen? 1, 2, 3, negative. If you're going to make a formula out of these two, what do you do? Lithium. That balances the charges. This is what I'm calling the simple ones. It's the metals whose charges we definitely know and a simple non-metal. The transition metal ones, I touched on this just before we left last time. It turns out it's something like iron. So that's down at that white part at the middle of the periodic table. The thing about this is it can be 3+ or 2+. So the transition metals can have more than one charge. So if I said, plus, Fe2 plus, and let's say I add, what should I use? I'll just use fluorine, which is -1. So what's the formula going to be here? Three. So you need 3 of these to balance that charge. This one would be Fe2. So there's literally 2 compounds. Naming wise, I told you about the ides: nitride, oxide, chloride, chloride, bromide, sulfide, phosphide. So all those have the IDE ending. And the positive one is just a name right off the periodic table. Iron, fluoride. So notice we end up with the same name for both of those transition metals. So when you're naming the transition metals, you've got to put in here a Roman numeral. It stands for this. So this is iron 2 fluoride. That is iron 2 fluoride. And this is iron 3 fluoride. It just turns out that it's this number because fluorine is a 1 negative. Let's do something slightly different. What's the charge on oxygen? What is it? -2. So what do you get for a formula for that? Okay, that's the one tricky one. Do this one first. If this one's -2, what's the formula here? FeO. No numbers are needed because they balance already. This is the one where you're going to have to think in terms of 6. So 2 of those and 3 of these will balance. Okay, so both of these are called, this is called iron 2 something, this is called iron 3 something. Here's oxide. So the difference in naming for the transition metals compared to the simple ones is when you have a metal that's from the transition metals, you have to put this in there to tell which one it is. And some transition metals can have like 5, 6 different charge states. Like vanadium has, I think, 7 different charge states. Okay, and one other twist here. What if I gave you CuO? So I give you the compound. That is a copper oxide, and I said, what is the charge on copper? Yeah, you can figure that out because you know this has to be -2, so this has to be +2. How about, I need to meet a periodic table. Anybody need a periodic table? Let's do. All right, what about this? What's the charge on chromium here? So think like this, there's 3 oxygens, -2, -2, -2. That's a total of -6 charge. That means that has to equal 0. So what can I put here to make this equal 0? +6. I have 2 chromiums, so I have to distribute that 6 among those. So these are each 3 plus. So you can call that.
So does that mean all chromium is like 6 or 3?
No, Chromium can have different charges.
Oh, it just depends.
That's kind of the point here. But if you can see the formula, and this has a definite charge, then you can infer what the charge is. There are different formulas. So you call this Chromium something. And what goes into parentheses for this one?
I'll just.
It's 3. It's the charge on the Chromium. That's so that's the twist with transition metals. Let me show you guys this. I don't know if I mentioned this last time. If you go to where those reading check questions are, here. You'll see more here than you'll see in what you've got. I've added a bunch of stuff for chemistry to practice. So that's really just there for practice. I won't make a grade out of that, but ionic compounds, formulas, and naming, we're going to get to Lewis structures and functional groups. Do I not have visible users? So that's there so you can practice your ionic compound naming.
Do you want to do this now?
No. Just to practice later. This is, oh, by the way, ever since I started chemistry, this is test 2 stuff. So this won't be on the test. Our test is Tuesday, right?
Oh.
It's over the reading check questions and then that last sheet I gave you on calculations.
There's a couple of quizzes where I can't like see my attempts. So like go back and look at them.
Oh, which ones?
I think it's chapter 1 and chapter 3.
Okay, I better fix that.
There's like
All questions with correct answers. I think that does it. Do you have your computer open now? See if that did it. It's 1 and 3, you said? Can you see it on chapter 1?
there's a lot of them that will just look at attempts.
That's what I'm trying to fix, so you can see your attempts. Oh, I gotta fix that one too then. Even if you can't see your attempt, if you do another attempt and just skip to the end, you should be able to see all the answers.
I did see it now.
Sig figs, edit. Okay. So now if you just try another attempt, you can see everything. Okay, just by trying another attempt, you should be able to see all the answers you know. So you can do as many attempts as you want and see all the answers. Did that fix it? So there's practice on there. Okay, the next thing, tell you, notice there were 3 in this list. There were simple, there was transition metals. Let's talk about the polyatomic ions. I take that back. Let's come back to those.
Somebody want mine, so roll the barcode. One bag one, so yeah, I applied for the arcade.
All right, we talked about ionic, let's talk about the way it is. Okay. One thing to do with your periodic table. Let's do. All right, there's something called those are the electrons that are on the outside of the atom, the closest to the outside of the atom, and they kind of have everything to do with, it's sort of like, if I said, what's the charge on beryllium when it's charged state? You would go 1, 2, so it's 2. It's those 2 electrons that it's losing. This indicates 2 electrons in the outer shell. Boron has 3 in the outer shell. Carbon has 4, nitrogen has 5, oxygen has 6, F has 7. Those that are in the outer shell, you can count by counting to the left. So I said, if I said how many valence electrons are in lithium, it's the same as that charge. It loses that 1 electron to become charged. It has 1. Beryllium will have 2. We'll do this. Potassium, sodium, these. My sodium looks terrible. These all have 1. These all have 2 in the outer shell. And then if I come over here to boron, it's got 3 in the outer shell, 1, 2, 3. Nitrogen has 5, 1, 2, 3, 4, 5. Carbon has 4, oxygen has 6. So you just put your finger on the atom and count to the left, and that'll tell you how many valence electrons you have. You with me? How many valence electrons does chlorine have? You just skip all the space in the middle and count to the left. What's here? Silicon, aluminum. I put my finger on chlorine and I count to the left. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 valence. You with me? That's how many are on the outside, and those are the ones that interact to cause the chlorine to do different things. Like for one thing, it's those on the outside for chlorine. You fill a shell by getting 8 electrons together. So chlorine gains 1 electron, become negative. Oxygen gains 2 to fill it up. But fluorine, how many was there before, or how many was there on oxygen before those 2 came along? Well, it's 1, 2, 3, 4, 5, 6. So 8 is sort of the magic number for these shells we're talking about. 8 fills up the shell. How many valence electrons are on sulfur? S. 6. In fact, everything in this row is 1 valence electron, 2 valence electrons, 3, 4, 5, 6, and 7. We can kind of skip those, but those have 8. Okay, so what we call sometimes called dot structures, sometimes called Lewis structures, or Lewis dot structures. So here's how you do a dot structure. Dot structure. If I want the Lewis dot structure for nitrogen, and this is useful because you can see a couple of things about the atom that's important for covalent compounds. How many valence electrons for nitrogen? 5. So what you do is go 1, 2, 3, 4, and as you come back around, you pair it. You just count the circle, and then when you get back to your first dot, you start pairing them. How many valence electrons does oxygen have? 6. So you go 1, 2, 3, 4, 5, 6. So that's the dot structure for oxygen. Fluorine. How many?
7.
1, 2, 3, 4, 5, 6, 7. So that's the dot structure for fluorine. As simple as that is, it gives you something that's very useful. I'll go on and do carbon. How many for carbon?
4.
1, 2, 3, 4. And hydrogen? How many valence electrons does hydrogen have? It's in the top left. Yeah, it's 1. It's just like lithium, except it's a non-metal, but I'll put it over here and go 1. Okay. So there's the dot structures of these. And the thing is, everything down below here have exactly the same dot structure because they all have 7. These all have 6, these all have 5, so they look exactly the same.
Oh.
One point to make is, the way I've drawn this was arbitrary. I've got a pair here, and 2 single ones. I could have done this, and that's perfectly valid. As long as it's got 2 pairs and 2 single electrons around it somewhere, it's a valid structure. I could even do this. That's still a valid Lewis structure for this. All right. Here's what you can tell from this. So we're going to start making things that look like this. Now that we're not talking about ions, ionic compounds. And you see here that carbon is making 4 different connections, 4 different bonds. Hydrogen, each hydrogen is only making 1. That's what you can get from this very quickly. It's these single ones that are by themselves that make these bonds. The bonds are really, let me simplify this. The bonds are formed by here's the dot structure of carbon. Here's some hydrogens that I'll strategically place with their. So what happens? So one of the forces that makes compounds is the ion, the atom becomes charged, and then when they're attracted to each other, they stick and make a compound. That's the ionic compound. The force that holds these together is this property that electrons can pair. So you see a pair of electrons there, a pair there, a pair there. This one's by itself and it sort of wants to pair. A pair there, and all of these want to pair. So that all of these single electrons here want to pair with each other. This is called the covalent line. Each line represents 2 electrons. One comes from one atom, one comes from the other atom. That's the covalent line. And it's just a completely different way that atoms can connect up. Only nonmetals do this. So that's why covalent compounds are made up of only nonmetals, because only nonmetals do this. But what you can get, if you just do that simple game to make the dot structures, you can tell this. Hydrogen makes 1 bond, carbon makes 4 bonds. How many bonds does nitrogen make? Only the single electrons do this.
3.
Makes 3. Bond, bond, bond. That will make 3 bonds. How many bonds will oxygen make?
2.
And fluorine only makes 1 bond. And hydrogen only makes 1 bond. So hydrogen only makes 1 bond, and everything in this column only makes 1 bond. Everything in this column will make 2 bonds. Everything in this column will make 3 bonds. And I'll go ahead, neon here. Neon, if I said how many valence electrons, you count across it and you go 8, 2, 3, 4, 5, 6, 7, 8. So now you can see what the full electron shell looks like. Neon has no single electron, so it makes no covalent bonds. Typically, there's some exotic reason why it will. But notice this. If I ask you what is the charge on fluorine when it's charged, you would tell me -1. Here's the point. That's neutral fluorine because it's got the right amount of protons in the nucleus to balance these electrons. But it can gain another electron because this shell likes to have 8 in it. It's called the octet rule, but the idea is the shell wants to be 8. So this one can become 8, and that's what makes it negative. But let me stick with this as a neutral atom. So that's back to the neutral atom. If I said, what's the charge on oxygen? And of course, that's true of everything down below it. If I said, what's the charge on oxygen, y'all would tell me -2. Well, the reason is I can squeeze 2 more in here and fill up that octet. So then it would be -2 charge. But it can also exist like this and make covalent bonds rather than ionic bonds. If I ask you what's the charge on nitrogen, you tell me -3. Well, here's those 3 negative charges coming in. They fill up that octet, now there's 8. So that's referred to in general as the octet rule. Okay. And here's one option you could make. So you could take these like a set of tinker toys and just figure out what can I make here. As long as it makes all the bonds it's supposed to make, it's a valid structure, meaning if I had a bunch of nitrogen and a bunch of hydrogen, I was going to try to start making molecules. So I'll pull this out of my tinker toy box and hydrogen out of my tinker toy box. I could do this. So here's 2 pieces out of my tinker toy box. I could connect those together. That's a valid molecule. It's called H2. We just call that hydrogen gas. But there's nothing else you can do there. There's no other connections here. So this piece out of my box and this piece out of my box, they're used up. I can't do anything else with them. But if I wanted to be more creative, because I took a nitrogen out, and I've got a bunch of hydrogen over here, what do you think I could make over here? Well, I could obviously do this. I could take 3 hydrogens, connect them together. That's a legit molecule. That's called ammonia. You could also call it nitrogen tetrahydride, but I kind of stay away from that name because we don't tend to name things that way. I'll teach you the organic naming when we get to it. How about this? If I took oxygen and some hydrogen, what would I make? There's a hydrogen that I'll connect there. I'm going to connect another hydrogen there. And we would call that H2O, something you've heard of. So think about just playing with these like tinker toys. What else could you make? Well, anything else in this row, I could replace the hydrogen with. Like I could have OF2. because it's only got one bond, just like hydrogen, so I could make that. NCl3, I could make. Okay. Or I could just stop there. That's a legit molecule too. You see what I'm doing? I'm just sort of playing tinker toys with these. As long as you use all the bonds that are there, it's a legit structure. You with me? Okay. Almost everything around you in the real world is made up of molecules, and almost all of those molecules are hydrocarbons, meaning it's carbon, some length of carbons with hydrogens. But every now and then there's some oxygen in there, and every now and then there's some nitrogen in there, and every now and then there's one of these in there. So you could also have something like that. Some of these might have a nitrogen on it. So I'm going to stick to carbon and build most of my molecules that way, just to simplify it. It isn't that other compounds don't exist without carbon, but this is just a good starting point. And I suppose I'll stick to, for now, all of these in the first row. These in the first row are by far the most common in the world. Nearly everything around us right now is made up of carbon, nitrogen, and oxygen. Maybe a little of this, and of course hydrogen. So let's build. A simple hydrocarbon. And I'm going to fill the hydrogens around. Okay. So I pulled out of my box 6 hydrogens and 2 carbons. So I can connect them up like this. And that does have a name, and I'll get to naming it in a little bit. Maybe I'll do that too. We'll see. Okay. If you wanted a formula for this, you would say C2H6. You see where that name comes from, that formula. We're no longer balancing charges. We're just naming everything that's there in the compound. So another way to contrast ionic compounds from covalent compounds. If you went and got some table salt and dumped it out, that's NaCl on the table, what you've really got is Na plus Cl minus, Na plus Cl minus, and I'm going to stagger these, Cl minus, Na plus, Cl minus, Na plus. So I've got positive, negative, and I alternate this way, positive, negative, Cl minus. And then picture, so that's 2 dimensions, and then you get into 3 dimensions. I'm going to take another Cl and I'm going to put it right in front of this sodium. So then I've got sodium, chlorine, sodium, chlorine, sodium, chlorine, chloride, I should be saying. So that 3-dimensional block structure, that's ionic compounds. And since that's the form they take on the microscopic scale, we don't call them molecules. That's a molecule. Covalent compounds make molecules. They make these discrete little units of a few atoms, maybe a huge number of atoms, but they're bonded together like this. Ionic compounds, there's really no individual little distinction for the structure. It's just, it can be huge, it can be kind of tiny, but it's going to be a lattice work like this. So you dump a bunch of grains of salt out on the table, you see that there's all kinds of different sizes. You can be as big as you want, really not infinitely big, but you know they'll form those little grains like that. So it's a lattice, not a molecule. And really the formula we use, once we figure out the charges and figure out how they'll go together to make them neutral, it's really saying for the ones here are sort of saying for every 1 sodium I have 1 chlorine. So it's really kind of a ratio, the formula for NaCl. if you had MgF2, it's really saying for every one magnesium in this big oblong crystal, you have 2 fluorines. So that's really a ratio of things to each other, in a sense. But this, when I'm here, this describes the discrete little unit that exists as a molecule. So the difference between ionic compounds and covalent compounds, at least sort of on a macro scale, is these can be just as big as they want until they break off. And then you have another chunk that's separate from that chunk. So they make these lattices, or molecules, are these discrete little things. So if I had a sample of ionic compounds, it'd be a bunch of little crystals like that. If I had a sample of this, it'd just be a bajillion of these sitting in a beaker. Not necessarily organized in a lattice structure. You see what I'm saying? Okay, so if I drew something like this is what I give it, this is how I do the formula. And if I had a big sample of this, I'd have one of these and another one of these and another one of these and just a whole bunch of those, and I could have them all in a beaker. Depending on temperature, it's either going to be a solid, liquid, or a gas. But I'll get to the phases later. Okay. So that's simple description. Let me do it. Oh yeah, I know what I'm doing. Okay. Let me, I'm going to break that bond. Break that bond. You can actually do this. These 2 electrons can slip down here and then be there instead. And these are going to go away, and you can make another bond. So that's called a double bond. So now there's 2 electrons in that bond, there's 2 electrons in that bond, and now we call it C2H4. That's a legit compound. And again, notice carbon is making 4 bonds. It's just making 2 bonds with this other carbon. If you took chemistry before, you recognize this. That's the good old double bond. And I can do one more. I can do a triple bond. I'll get rid of that. I've got these 2 electrons left. They slip in here, and you're making triple bond. And that's it. There's no more. You can't make a quadruple bond. So that formula would be C2H2. So there is such thing as C2H6, C2H4, and C2H2. The difference is the bond. So triple bonds. You guys with me? Let's try involving nitrogen. I'll start like this. There's the Lewis dot structure. There are a few carbons. Pull the nitrogen out of my box. I've got nitrogen like this. That pair of electrons just sits there. It doesn't do anything. This pair. But I can do this. I can go connect those 2, connect those 2, connect those 2. Now I have these sticking off. One thing I could do is either use hydrogens all the way around or some combination of hydrogens and these. This column of fluorine, these are called the halides. So I could do hydrogen or any of the halides and just sort of truncate the molecule right there. I suppose I'll just stick hydrogens on here. So there's 2 lone ones here, so I'm going to do this. Every carbon's making 4 bonds. The nitrogen is making, it's required 3 bonds. That's a legit molecule. And if you wanted to know the formula, C3. For hydrocarbons, we usually do the C and then the H's and then anything else. So I would say C3, H, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'd stick an N on there. And this is another one of those situations where you'd expect me to put a 1, but for some reason chemists don't put the 1. If there's just one there, they don't put a number. So that's the formula for that, C3H9N. And there is a way to name these, but I'm going to hold off on naming. How about this? I can do this. What if I get rid of that hydrogen and that hydrogen and make them go away? Now I can make a double bond with these two electrons. So that's a legit molecule. That would just be 9, 7. That's a legit molecule, C3H7N. You with me? And you can actually, you remember when I said it didn't matter where these were drawn, just as long as there were two single ones and two pairs? I'm going to move this hydrogen down here. Now, I want the hydrogen up here in the pair out of my way, so I'm going to redraw it like that. And now I'm going to do it again. I'm going to make a triple bond between nitrogen and carbon. I can remove those. These two with their electrons go away. And they'll find their fortune in the universe by themselves. Take these two electrons, bring them in here. I can actually make a third bond. But again, 3 is as much as you can ever have. There's no such thing as a quadruple bond. So that's another legit molecule. Now I only have 5 hydrogens. What's that? So that's kind of a basic introduction to molecules and the way they work. You can have double bonds, you can have triple bonds, you can have single bonds. There's way more variations than I can do here. But I'm going to stick with carbon and hydrogen, hydrocarbons. Sometimes nitrogen, sometimes oxygen. I'll say this. For our purposes, we'll use carbon, hydrogen, nitrogen, oxygen, the halides, and I have to stick sulfur in there too. So basically what I'm doing is I'm walking you into organic chemistry. Organic chemistry ignores the entire periodic table except for those. In some sense. Organic chemistry really stumbles into other things, but the fundamentals of organic chemistry is only these atoms. And that's because the organic world, the world we live in, is almost completely made up of only that. I'll put it like this. We'll put it this way. If you're standing in the woods in the middle of nowhere, there's no technology around, everything around you is this. Just about everything around you is made up of this. The trees, the plants, most of the dirt because it's worms and organic matter down in there. If you want to know where the ionic compounds are, so these are covalent compounds, is what I'm saying. It's the covalent compounds and specifically these organic ones. If you want to know where the ionic compounds are in nature, well, you dig down about 10 feet, you start finding ore and stuff like that. That's where all the ionic compounds are. Of course, you see some rocks at the surface, so I guess ionic compounds count there too. But that's it. You don't tend to find metallic compounds. You have to make those. You have to find the ore with the metal. And the metal that you're finding is in an ionic compound. You heat it up, it melts, and you can make your metallic compound. If you're not standing in the woods, if you're standing, say, here, in the world we live in, it's still largely true that everything around you is made up of this. Just about every synthetic fiber and everything that human beings make is still almost all organic chemistry. So that's why organic chemistry is a thing. Chemistry there's physical chemistry, which is my background. There's instrumental chemistry or analytical chemistry. That's using instruments to analyze stuff. And then there's organic and inorganic chemistry. That's the 4 major areas. And the reason there's a whole area is because so much of the world is just this. All of biology is this. Your body is pretty much all this. There's some ions that your body uses. So anyway, organic chemistry is kind of where I'd rather take us from the broader area of chemistry. So in here, like, you can find some ionic compounds. Usually I'm in a room that has what do you call it? Whiteboard? What do you call that? What do you call it? I can't think of it. That most walls are made of. It's like gypsum or whatever. What do you call that? You've heard it before. What walls are made of?
Walls.
Yeah, what do you call that?
Like.
Something board, not these walls because they're concrete, but in a house. I can't think of it. You know, you get a new house and you bring the guys in and they install the white, nice walls. What is that? What'd you say?
Is it cardboard?
Drywall.
Drywall. That's it. That's mostly gypsum, so that's kind of an ionic compound. And I suppose because this is stone, that's probably mostly ionic, but everything else in here, like you can identify the metallic compounds. It's like the things that go cling. So there's a good bit of that in here. But everything else, including you and your clothes, are organic molecules. So just as a perspective, why we would focus on those, because really, a huge chunk of the world is that. Synthetic things like synthetic fibers like nylon, again, mostly that. I think this is a synthetic, these laptop things, that's some kind of polymer, which again is very much all that. Okay. Okay, I'm going to swing back to ionic compounds real quick. Because to understand what polyatomic ions are, you have to know what these are. So let's swing back and finish up ionic compounds. I said there's the simple, there's the transition metals, and then there's polyatomic one. So before we would go, I say, what's the charge on lithium, or what's the charge on this? It's a single atom and another single atom when we put them together. Polyatomic means there's a covalent compound, not on iron. It's one of those covalent compounds that I was just showing you. But it turns out the electrons and protons are not balanced. So it ends up with a charge. There's only a handful of important ones. I will give you this on the test, but this is just used to make one stuff here. I will give you this on the test, but we have to finish up ionic compounds with the polyatomic ions. But it's a covalent compound that happens to be charged because of the imbalance of electron and proton. But it's the same exact game we've been playing. But this will show you the charges, the atoms involved, and the names. And like I said, I do this on the test. You don't have to memorize it. I count down one side of the table. The important polyatomic ions. Okay, for instance, the one that says acetate, I'll show you the structure. It says C2H3O2 is. I'll go ahead and draw that. That we would call acetic acid, that structure. It's called an acid because a proton will pop off of it. But what happens is this hydrogen leaves behind this electron. It ends up positive. Both of the electrons that were in the bond to it end up here on the oxygen. And that ends up being negative. So anyway, that's acetate. You don't really need to know that. I just wanted to say this is what polyatomic ions are. They're molecules that happen in each other. So that's like one of the oxygen making a double bond, 2 bonds for oxygen. Oxygen's only making 1 bond here, and it's supposed to make 2. That's kind of suggestive of the reason of how we get the charge here, but I don't need to go into that. carbon making 4 bonds, hydrogen making 1. But if you wrote the formula of that, you would get C2, H3, O2, and then you put the charge there. So that's what you see there for acetate, the formula for acetate. But I just did this to emphasize that these are covalent compounds that happen to be charged. Okay. And the way you use this, pretty simple, because you've already got the basics. If I said, calcium carbonate, what's the formula? And calcium is this, Ca on the periodic table. You look on here, you find carbonate, it's the second one down under acetate. It shows you this, CO3. This tells you the charge. This tells you what you're going to write in the formula. What's the charge on calcium? Yep. I do expect you to look at the periodic table for that. I mean, I know this because I've done this for years. That's why I give you, so you look at it and see if it's 2 plus. So this is 2 plus and that's 2 minus. So what you would write is CaCO3. That's the formula for calcium carbonate. The tricky part when you're looking at the formula is to pick out these, and that'll mess with your head a little bit. If you don't see just 2 things together, you see the metal and then some other stuff, then you can go, okay, it's going to be on here somewhere. And so if I gave you that and said, what's the name of it? You'd go, well, I see calcium, and then you go, what is all this? And your brain's going to blow up. Just realize you're looking for that. Break the calcium off, look for that on here, and you'll find carbon. How about yeah? What if I did? Calcium nitrate. So this is Ca2 plus. You look for nitrate on here, and then you find NO3 minus. So now you're going to make a formula out of it. So I need 1 of these and 2 of these. What you do here is you use parentheses, so I can put a 2 there. If I tried to do it without the parentheses, I'd have CaNO3, and then I'd have to go 2 like that, and it's really confusing and weird. That's why we use the parentheses to indicate I have 2 of these. I'm literally saying that I have one of those lattice arrays that goes Ca, well, I just do it like this. That repeats somehow. That's the formula. For every 1 Ca, there's 2 NO3s in that lattice. When it's charge 1 and charge -1, the lattice is easy to draw, so that's the example I use. They get kind of weird and exotic when you have to do, how do you balance 2 things with 1 thing and still make it symmetrical as a lattice? It's doable, but it's kind of a full discussion. Okay, calcium nitrate. Okay, how about iron-free nitrate? Notice I couldn't just say iron nitrate, because iron can be +2 and +3. I'm not expecting you to know the 2 charges that iron can have. You don't have to memorize that. Just realize you're going to have to infer the charge somehow. But iron nitrate, iron-free nitrate, that means we have iron-free and nitrate. So how are you going to do this one? Start with Fe. I've got +3 here and -1 here. So how many nitrates do I need? Charge +3, charge -1. How many nitrates? 3. I'm going to need 3 of these to balance this charge. So I'm going to go NO3, but since I need 3 out of them, I'm going to go like that. I'm going to use titanium. Ti is titanium. What if I had Ti is right here at the top of the transition metals on the left. Let's see. What was I doing? CR4. Okay, that's titanium, that's chromate, so this would be called titanium chromate. But it's called titanium. Suddenly forgot how to spell it. Titanium. Since that's a transition metal, I'm going to need something in the parentheses here. So let me ask you, what's the charge on titanium here? So you do this. Can you find chromate on there? Did you find chromate on that list? What's the charge on chromate? So you have CrO4 minus 2 and CrO4 minus 2. You have two of them. See what I'm saying? That means you have a total charge of minus 4. What can I put here to make this 0? Plus 4. I only have one titanium in the formula, so that means that whole charge goes there. So that means Roman numeral 4 is this. Y'all know your Roman numerals? Roman numerals are weird. So this is called titanium 4 chromate. Titanium. And 4 chromate. Okay, I looped back to finish polyatomic ions. So really, I think we've done all I intend to do with ions. So you'll have to be able to come up with the formula if I give you the name. You have to come up with the name if I give you the formula. And sometimes you have to infer the charge of the transition metal, like this case. I would say do exactly the way I do. I tabulate this, set up my formula like that, equals 0, and then I go, what goes here? Let me do one more of those just to remind you of how I do this. How about this? No, that doesn't kind of work. Okay, I know what I want. You guys want phosphate. PO4. Okay, this is fun. So this would be titanium phosphate. If you look for phosphate or you look for PO4, you find it about here, phosphate. What's the charge on phosphate? So the question is, how do you name this? And because you see that this is a transition metal, you go, okay, I got to find the charge on that. So you got to go through that first before you name it. So what's the charge on PO4? 3 minus. So I would go PO4, 3 minus, PO4, 3 minus. No, there's only one of them. I meant to do. Yeah, I meant to do that. I meant to have a 3 there. That gives you a total of -369. trying to do one where we have, I'm gonna put two of those. I want it to be, hold on. 15, 15. I'll just go back to an example I used the other day. So iron is a transition metal. Why can't I do this on the side? If I want that to be +3, that would be 6. Let's do that as 2. So I need to charge 2 here. Go back to CR4, chromate. Okay, doing the same thing we did here. We've got iron, something. So to finish out this name, I'm going to need to put something in the parentheses because that's a transition now. What's the charge on chromate? CrO4. It's right here.
2 minus.
So I've got, I'm not going to write them in. 2 minus, 2 minus, 2 minus. There's 3 of them, so I've got these. So I've got a total of -6. It has to equal 0. So what do I have to put here to make this equal 0? Plus 6. I've got 2 FEs. So I've got to distribute the 6 among them. So you just split it in half. You go half the charge is here and half the charge is here. And that tells you this is iron 3. See? Okay. I dipped our toe into covalent compounds, but I think I've done all I'm going to do for now for ion compounds. That'd be good. We'll start with covalent compounds, I guess, next Thursday. We didn't really review I guess we reviewed the calculations. You guys think we'll be ready for the test too? I can't think of anything else we can really do. That last sheet I gave you with calculations, and I put up the answer keys, practice those questions for the test, and then the read and check questions.
What chapters will we have?
Just the ones we did read and check. Yeah, yes. And just study the read and check questions.
Do we need a scan shop for class?
I'll bring it.
Okay, thank you.
Just show up.
Thank you.
Maybe bring a pencil. I'll have pencils too, though.